Good morning, good afternoon, good evening, everyone, and thank you all for being here today. My name is Charlie Collius, and I am the Product Marketing Manager for the Equipment Group here at AFL. And today we have a very informative splicer presentation for you. Craig Henderson is a Senior Applications Engineer at AFL, and he will present Mastering Fiber Splicing, Overcoming Tolerances, and Technological Challenges. But before we jump into the presentation, I would like to introduce the other half of our Splicer team here for a quick intro and to go over some housekeeping tips. Take it away, Mega.
Thank you, Charlie. My name is Megasham Garlapati, and I am the Associate Product Line Manager for the Splicer team in AFL. I will be co-hosting with Craig Henderson here, and I'll be helping out with the questions as you are posting in. So before we begin today, I just want to go over some housekeeping tips. Today's slide deck is available to download by clicking the handout box in your control panel. And there is a PDF right there called AFL's Mastering Fiber Splicing, Overcoming Tolerances and Technological Challenges PDF. So you can download there and you can follow along. Also, all attendees here are in listen only mode, so that we can reduce the background noise during the webinar. If you have any questions during the presentation today, please feel free to submit it in the question box in the control panel on your screen. So there is a Q&A there, and type them right in there, and we will answer them at the end of the forum, or as we go through the slides, and if anything pertains to it, we can surely answer there. Today's webinar is being recorded and should last about 45 minutes, and the link with where to view the recording will be sent out in the next couple of days, along with a certificate of participation. Also note, there is no CEC credits for this one, so we will be sending out a certificate of participation with the survey after a few days. And with that, I would like to introduce Craig Henderson to start today's presentation. Craig, all yours.
Thank you, Mega. Charlie, appreciate the introduction. I'd like to kick this off pretty quickly from the stand of this is going to be a kind of a real world presentation. This is something that we are constantly getting questions about, and we certainly want to enlighten both the builders, the owners of the systems, and the contractors that are doing the work for the teams. So we'll kick this off, and okay, so where do we start? This is going back to when I started with the company in 1985, how these systems were built. For most purposes, the fiber that was introduced was what I don't want to say a generic vanilla because it's very complicated in its structure, but it was a ITU standard G652D fiber. This fiber, normally in the industry, is called SMF, single mode fiber. And as it was being built, your telephony companies, as they were installing this, were basically developing rings in the industry. And if you look at the slide, you'll notice that how it is simple. And this G652 fiber was very simple to splice, but it was used with EDFAs, optical add drop. The rings, as you can see, are in color. So we were able to produce multiple waves over this glass and basically build this system from A to Z. What has happened since that time is that during these splice processes, when we would do repair and installations of this homogeneous fiber, because it would be used in the central office, the outside plant environment, all the fiber was basically the same flavor. It actually required very little simple parameters with your splices, test parameters, all that stuff was kind of generic across the board. Since that time, and where we're at today at the present moment, is enhanced fiber designs which allow deeper network reach and higher data speeds. The main player in this, especially in the high density areas, is the ITU G.657. This fiber, they call it BIF or BIF, which stands for band insensitive fiber. This will allow you to do some pretty intense packaging, and we'll get into the various products that this was used in. But if you look at the schematic, as you can see, that we're going through various components within the system. You're coming out of your head ends, your central office locations, you're combining voice and data, sending that through an OLT and your typical PON network. And that would be fitting in these very tight building constructions with patch panels and the various components in the multiple dwelling units on the tail end of this. So it requires a new style of fiber being developed for that, and that is, again, this G.657. On the long haul systems, another fiber has come into play. This is your G.654. This particular product is designed for high data rate transmission, where you're actually using the 1550 nanometer window to transmit dense WDM systems long distances at very high data rates. So we've got these various combinations now that we're going to have to splice together: the G652, the G657, and the long haul 654 fiber. How does this affect installations? First of all, it actually has gotten simpler. The technicians and the outside plant deployment crews and the construction crews are allowed to use tighter and tighter packages. As a result of this, this G.657 fiber, this bend sensitive fiber, it will allow you to increase your density quite a bit with the cable constructions. The cable constructions, as you see today, are gel free. They have no buffer tubes. They're thinner cable jackets. We use quite a bit of this cable in the industry today, and it's all about getting more fiber in smaller cross-sectional areas. It also is heavily benefited for you as you move into your packaging for splice closures, patch panels, pads, the smaller termination options you have out there. The 652, the old legacy glass, was very much bend sensitive, and you're using a fiber that would, you couldn't bend it more than 30 millimeters in a small package environment. Unfortunately, this would cause a lot of macro bending, optical loss as a result of those tight turns in this very tight packaging. So this G.657 style bending sensitive fiber gives you a lot of advantages in the packaging that you can bring to our customers today. Now, technical considerations as far as splicing testing. Splicing considerations. What you see on the screen here, and I'm not going to tell you which side is which, left or right, we're going to come to that in a moment, but we have two different fiber types. The images you see in front of you today is a mass fusion where you've got 12 fibers on the left, 12 fibers on the right. One is a 657-A2, which is BIF fiber. When it says R7.5, that means your bend radius for this particular fiber, without losing your optical characteristics, you can bend that to 7.5 millimeters. The fiber on the other side is a 652. If you look at the image as you see here, which is a cold splice image, you don't see any difference between those two glasses. They look identical. The characteristics as far as physical dimensions are identical. Both have 125 micron cladding diameters, and that's what you see on the monitor. However, as we move to arc these two fibers together and have a warm image splice, you will see something dramatically change. During this arc process where you are actually heating the glass, you will get what I call luminance coming off that fiber. And you will notice the fiber on the left, which is the G.657.A2 glass, as compared to the right fiber, which is the 652D fiber. You'll notice the clear demarcation of the brightness, and that center line right down the center actually indicates the splice joint itself. So as a result of this, what is happening is let me back up one second, is that you have several things happening in this splice joint. During the arc process, you're heating this fiber up to approximately 1600 degrees centigrade, and you're melting those two fibers together. The characteristics, if you look at the spec sheets on the 657 and the 652, you want to have a slight difference in mode field diameters, but you also will have some difference in the dopants and the composition of the glass on the left and right side of those fibers, and you will have a little bit of mixing of that splice joint. Now, this is one type of 657A2. I'm going to click and move on to a second OEM's G657-A2 fiber. Here, you'll notice that the difference in luminosity between the left and right fibers are almost identical, with the 652 and the 657 being the same. So it's not, how do I say, every OEM, every qualification of ITU spec fibers will have the same glow pattern characteristics. So there is some variance in the industry, and you will notice this during the splice process. This particular page is actually very interesting. I'm going to play a couple of video clips for you. One thing I would like to point out on the left-hand side of the image here is a refractive index profile. This particular chart was produced with a analysis machine that would allow us to map out the refractive index characteristics of the fiber. So you'll notice here we have two lines. The black line is the G657 fiber here, and then the red line is the G652 legacy single mode fiber. The refractive index properties of these two classes are very closely matched. You'll notice here as it drops down, this is from here to this point is actually the cladding edges of the two fibers. And then this bright region you're seeing here is the outside core cladding transition point, and that very center line is actually the core of the fiber. I'm going to splice this fiber together through this little video clip, and what we have here is a G652 to 657A1 sample A. I'm going to make the splice, and you can see a slight line between the, ever so subtle in this area. This is very normal with this machine. You'll notice the loss estimation is a 0.01 dB. Very good quality splice here. And by the way, the chart on the bottom is actually a splice loss distribution chart of 30 splices. And you can see here, even though you're splicing this 652 to 657, the actual loss distribution is very good with this active profile alignment system you see. I'm going to take this video and I'm going to slightly back it up a little bit, and I will just pause it here. And this is the luminosity of the two fibers coming in. The left fiber is 652. The right side of this fiber is 657. And by the way, the two images you see here are actually two axes of view, the X field of view and the Y field of view of that splice. I'll move over to the next splice, which is sample C. I will point out here that this particular 657-A1 sample from one of our OEM suppliers has a slight area of depressed cladding associated with it, and the refractive index of the cladding is slightly lower. So when we make this splice, let us play this out. Again, you can see that line between the splice on both axes. Very good core alignment. I would like to point out one of the great benefits of an active profile alignment system is that you're magnifying this fiber approximately 165 times on two different axes, and it gives you the ability to see that this core is parallel both on points of view. So this loss estimation combined with the what your eyes are telling you, you can have a fairly great deal of confidence that you got a high quality splice here. Again, notice the optical losses on the bottom, actual charts, the minimum 0.02 ranging up to 0.07 dB for this particular splice. And I will back this up a little bit also to show you the luminance of that particular splice. I'm going to move over to the next page. And we got two more samples I would like to show you. Is we're moving over to a different style of G657. Notice here it says B3. This can sometimes be considered like a UBIF fiber. You'll notice that it has a very deep trough associated with the cladding before it gets to the core on both these samples, but this type D fiber, when I make the splice here, you can see these two heavy lines. You will see a fairly significant image on the splice, and a lot of times in the industry, this is interpreted to be a poor quality splice. In fact, if you look at the dB distribution loss on the table below, the optical characteristics of this type of splice is still fairly good and certainly acceptable with most standards in the industry. But you do see this heavy defined line between the splice. If I back this image up and you go back to the core, you can see the luminance difference of the 652 as compared to the 657- or point B3. This particular splice, I will point out on some later slides, we actually have some OTDR readings and some splice loss data associated with this splice that we actually recorded. So when I reference sample D later in the presentation, it is this splice that we will be showing. Let's move over to our next splice, which is a different vendor's 657-B3. As pointed out earlier, this 652 fiber is the same fiber through all four of these splices that have been made. Splice loss distribution is still fairly good, as you can see. But again, a lot of the industry would interpret this to be a defect and would be a rejection of this fiber. I can tell you, when you do see these luminescent characteristics, these warm image splices, when you see this type of differential during the splice process, it's going to more than likely show up on the backside when you do your OTDR testing. Testing your network. Okay, so that sample D splice that we had made earlier, what you see is a image that is created through our TRM software using a FlexScan FS200 OTDR. We had tested it at two wavelengths, both at 1310 and 1550, but for this purpose of this presentation, we're going to be discussing the 1550 characteristics. So this splice that I mentioned earlier, the sample D, if you're out in the field and you're doing a unidirectional measurement, depending on what side you're measuring from, you can see a loss as great as 0.353 dB. This is actually a recorded loss in this splice. And that is shooting from the A side to the B side, or from the G657 side of this splice. Of course, this is not going to be compliant with most, if not all, the network standards. Nobody would ever accept a 0.35 dB splice. Again, unidirectional measurement. That same trace in the opposite direction where we sent A to B, we're now shooting from B to A back, and you will notice this splice has a significant gainer now, 0.271 dB. So let's discuss why this happens and the nature of an OTDR. Okay, the OTDR, optical time domain reflectometer, inject pulses of light into the fiber and measures the backscatter to characterize length, loss, and reflections coming from that network. I just call it kind of like a sonar for fiber. What will happen to this when the backscatter is similar from fiber to fiber? So if you're doing a homogeneous fiber like a 652 to 652 splice, the backscatter characteristics of both of those glasses are pretty much identical. And that unidirectional measurement for splice loss would more than likely be fairly accurate with an OTDR. But in the cases today in this industry where you're splicing 652 to 657, that certainly may not be the case. The reason this happens is the backscatter characteristics are different for each fiber. And if you look at the different types of glass, you have different backscatter. The case of the image on the top is a homogeneous splice, splicing 652 to 652. So it will mimic an actual splice loss in one direction. Older fiber typically has higher backscatter than newer fiber of the same type. Also, part of this calculation is the mode field diameter. We hadn't talked about that much, but back in several years ago, when I saw a gainer or a huge loss with an OTDR and we had a mismatched fiber type, I associated that with mode field diameter only. That is not actually accurate. Mode field diameter certainly has some feedback to the OTDR as far as the gainer and the loss, but it actually is the backscatter characteristics of the glass itself, that luminance coming off that fiber back to that photodetector of the OTDR. I got a big don't panic here because it really no harm, no foul with the splicer. It's just how do you interpret the data with the OTDR. So that particular splice, that sample D that we described earlier, to calculate that loss is actually measure A to B. That's where you got that 0.353 dB. And then you measure from B to A, and that's where we got the gainer of 0.27. You take that data, add it together, divide it by 2, and the actual splice, that image you saw on the sample earlier is 0.041 dB, well within acceptable limits for that particular scenario. It's a perfectly acceptable splice. And the beauty of this now is modern reporting software can calculate this stuff very quickly for you. Kind of describe bidirectional network test configurations and why we set up our OTDRs to accommodate these bidirectional losses and be able to print those reports really quickly for you. First thing you'll notice here, the launch cord itself, the launch cord is on the front section of your OTDR and go to your side A, or the first connection on your test device under test. You would use this launch cord in order to get away from the dead zone of your OTDR and clearly be able to see this AN connector. On the tail side of it, we also would use a tail cord. So this is telling the OTDR that we have a 150-meter tail cord on the back side of our device under test. This will ensure that the B-end connector, the connector on the tail end, would also be able to be calculated to give you that end-to-end loss that you are seeking. You'll notice here when testing bidirectionally, the first connector in one direction is the last connection in the opposite direction. Here is a combined report. Again, this is coming from an OTDR, so you would do your A to B test, you B to A test, you would dump that into your cloud, pull this information off, and it would clearly document the splice losses and give you that bidirectional average on the bottom there, which is 0.041 dB for that sample that we described earlier. Very easy to operate. I will tell you that bidirectional testing requires an operator to be on both ends because, again, you're putting that tail cord in sequential order with the launch cable in order to record these particular fibers in the test sequence. What about OLTS testing? This is an optical light source pyrometer. This phenomena that you see with gainers and losses and the backscatter characteristic does not affect an OLTS meter. This only occurs with an OTDR. The link loss with an OLTS shows true link loss. No one direction loss or gainer is associated with this type of test mechanism. Why? It's a difference in technology and optical differences. First of all, an OLTS OTDR is like comparing apples to oranges. They're two distinct optical systems. With an OTDR, you're using a kind of a radar effect. You're launching a pulse of light. You're waiting for that light to hit certain defects and anomalies and bounce that photon back to the photodetector to record your information. Where a light source and pyrometer OLTS system is measuring output power in a constant light source. Troubleshooting dissimilar fiber networks. Really, an OTDR is used to find location faults, kind of employ pinpoint types of locations and where they located in your system and provide you accurate footages where you can go locate those particular phenomena. Now, how do you know the mode field diameter mismatch or backscatter? Again, I use those two terms interchangeably, mode field mismatch and backscatter, and whether it's a fault or not. If you see a gainer, it is due to a mode field mismatch or backscatter effect of splicing mismatch fiber. No other events can cause this type of gainer. You'll also, when you're in a network, and I've seen this many times in the industry, the network, what you have, they come in pairs. You'll notice see this gainer, and you'll see this loss on the other side. So this particular scenario is you may have a down circuit and you have to come in and splice an old cable to a new cable. And this is an illustration of that, where you may have had some pole damage and you had to replace a section of cable, and you had different glass classifications in that new cable, and you will see that crop up in this particular image. I actually seen this happen in central offices as well, with patch panels and new customer premise cables in a central office environment also. Typical faults have higher losses or event reflections due to air gaps caused by a fiber break. So this statement really is telling you, if you do have a true fault, you would normally have a fiber break, you would have a large Fresnel reflection, you have a large spike at a point, and that would indicate that you certainly have significant damage in your device under test, and that particular location could be pinpointed with the cursors and give you a very accurate distance measurement with the OTDR, and you could locate that a little bit easier as a reflection of finding that high back reflection and finding that location. BFLs, this is interesting because we do get these comments and we do see customers sending us photographs, and what happens with a BFL, you're looking at a splice and you think you have a poor splice as a result of excessive scattering. The image you see on the far right hand side, this is actually a quality splice, but you've got two different styles of fiber. You may have a 652 to a 657, and the BFL is actually illuminating as it strikes that new fiber composition. And I've seen this many times, and you say, wow, I've got a fiber break there. In reality, that may be just the mismatch cladding compositions of the fiber you're being spliced, and it will be repeatable. If you've got 12 fibers in a splice array, all 12 fibers would exhibit this same type of phenomenon, same luminosity coming off the BFL. Wrapping up, let's talk a couple of things here. Optical fibers have adapted, and they are very useful in today's environment. I can tell you, we wouldn't want to be building these tight structured networks with the legacy 652 fiber. We'd be constantly battling macro bin issues across the board with all these applications that we put fiber in. It's really a non-issue. It's just a matter of the OTDR and the mechanisms that play and how it measures optical loss. As you test them with the OLTS meter, you wouldn't see a problem at all. Or you do bidirectional, you wouldn't see a problem at all. Much time is wasted in the field due to lack of knowledge about this phenomenon. So all these folks on the call today, be sure to share this information with your fellow team members, and let's get everybody trained as much as possible. You will see the presence of G654 fiber is gaining ground in terrestrial applications. They used it in subsea for quite a long period of time, but you're seeing this G654 fiber being deployed, and anytime that is spliced to the legacy 652 or even the 657 fiber, you would have some of the types of occurrences occur in the future. I would also strongly know your network, know the types of fibers being deployed out in the in your networks. And I think one of the most crucial things, because I'm almost dealing with this conversation with contractors on a daily basis, and it is the conversation of the contractors writing a contract doing the splice and they get to the point of doing the test and inspection, and there's no conversation about whether unidirectional OTDR measurements are a requirement or not. I strongly recommend that these conversations happen between the owner of the system, the construction personnel, including contractors, to understand, these are irregularities, these phenomena, and if they want an accurate test report, they're going to have to do bidirectional OTDR testing, and it's going to require some expense, tying up an extra technician, tying up the extra hardware to perform these tests. So hopefully we can have these discussions on the front end to avoid any types of hard discussions on the back end. Thank you for the presentation. We can answer some questions now, and thank you for your time.
So, hey Craig, great presentation. So we got some questions here lined up, and to start with, what splicer have you used to test, and what the screens which you shared in the splicing, what is the splicer? What model is it?
The model shown, of course, with the mass fusion splicer, that image come off our mass fusion splicer. Is called the FSM 90S mass fusion splicer, which is a fixed V-groove system. And it is designed for capacity where you're splicing 12 fibers at one time. The reason I showed that image is I wanted to show the distinction between the two luminance characteristics coming off the 652 to the 657 fiber. That was a mass fusion splice. The rest of the splices were made with the Fujikura 90S active core alignment system. This system has been one of, I guess we had 10 iterations of core alignment systems. Fujikura developed the first active profile alignment system in the world. They have controlled very sophisticated algorithm software. That system has the capability to actually discover the pinpoint location of the core residing in the cladding. So if your fiber has core cladding concentricity issues, that machine can detect that core in that cladding and make adjustments to compensate for that particular defect in your glass.
So as you are in this topic, what splicer do you recommend for when you have different kind of fibers splicing together? Will a core alignment splicer work out, or a clad alignment splicer?
That's a good question. And actually, I don't have a recommendation other than what is the owner's expectation on quality. If you're telling me that you've got to achieve a .02 dB, a .04 dB splice, then I would definitely look at those loss characteristics that we displayed, and maybe come back to the owner of the system, say that's probably not going to be achievable based off of these loss characteristics. If you go into that scenario, please reach out to us and we'll be able to kind of give you a little bit of guidance on the combination, the expected splice loss. But if you're trying to achieve the ultimate splice as far as optical quality, you can use the active core alignment system. If you're in the industry and you're trying to get anything below 0.2 dB and you're on a budget, a clad alignment system would work fine for you, such as our 45S clad alignment system at that point. Or you could even use mass fusion.
Awesome, thank you. And we do have some questions regarding the testing. So there is a question asking for, so when a FiberTech uses high power single mode light, can that break down a splice over time?
Interesting question. So if you're getting into a extreme high power, there is some YouTube videos out there. This one is called Fiberfuse. If you actually do a search on that, that's showing a high power laser pumping into an optical fiber, and the fiber looks like somebody had lit a fuse, and it's degrading as a result of that power coming through that glass. So there always needs to be safety precautions in knowing the system you're working with. And it could be detrimental to a splicer. It could be detrimental to an employee in that environment. So be very cautious and know the system you're working with.
Awesome. Yeah, true. I agree with that. And is there a maximum allowable tolerance for fiber splicing in a bidirectional test if you're measuring from one side of the fiber?
That's a good question. Of all the splice testing that I had done for this particular paper, the event of that 0.31 dB was kind of on the higher end. So if you have a unidirectional and you're doing 652 to 657, especially the 657B3 fibers, you probably would want to be the higher end of that unidirectional measurement for that particular case, which would be 0.31 dB. Unfortunately, I don't think the owners of the systems would allow that type of one directional loss to be approved and then make payment for it, right?
True. Yes. And maybe it's in the specifications of the project. Each project can be spec'd out in a different way too.
Yeah, that kind of ties back to having the tough conversations with the owners and the work that's being done to clearly define the expectation of the splice loss on the front end. Because again, testing in the field is expensive, and we need to have that discussion on the front end.
Got it. And are there any major issues that prevent using different types of fiber? And is it recommended to use same type of fiber in a network?
And that's an interesting question, because I don't think there is any net ill effects with using different variations of glass other than the speed properties. If you're running a high data rate system, you would definitely want to have, fiber that can carry that data rate systems. If you're dealing with high density scenarios, you would definitely use a 656. I know when we build pond cabinets here, our pond cabinets are built with G657 A2 glass. When we're building cable constructions that require 3,556 fibers in a single cable, we would use a bend sensitive fiber just for packaging considerations. So it's here to stay. It's just knowing what those systems are. So 652 to 657 to 654, you may have a little bit of an optical loss penalty, but in reality, it's a small number in the grand scheme of things and the loss budgets around most systems.
Okay. And just a reminder, I have got a lot of questions in here. I'm just funneling with the ones which are very close to our presentation today, but we will get back to each of you to answer the questions. So are the claddings from different suppliers in this generation are that different that it may affect the splice and the quality of the network? And we understand that different cores may give some problems, as you were explaining, but what about the claddings?
Interesting question. On the telecommunications side of this, and when I say telecommunications, I'm talking about utility groups, data centers, the typical telco company. The fiber construction really comes down to claddings being 125 micron. The core can vary from a multi-mode variation, which is used in data systems or very old systems in the network as far as in the central office. But the majority of the cable these days is a 125 micron cladded fiber with a single mode core. And that single mode core is typically tuned for the macro bending issue with the BIF fiber, or is tuned to the low optical characteristics in the C band, which is that 1550 nanometer window to carry fiber transmission a very long distance. That being said, you get into coating diameters, that type of material, the industry is changing quite a bit on the coating diameters. So when somebody asks me about splicing fiber now, I ask for the fiber specification. I ask for the coating diameter, because you're running into a lot of the legacy fiber is 250, but a lot of the new constructions now are 200 micron coated fiber. We're getting into rollable ribbon fiber now, and that not only has coating diameters, but it's got pitch spacing. So there's quite a number of variables here. So when you're talking to me and my role as a senior application engineer, I have to get a lot of information to make sure I'm providing you the correct splicer product along with the correct accessories for the splice, making it very easy to splice and make it very repeatable to splice. That's kind of what we're trying to achieve. You can get by, I call them grades of quality. You can get by with less accessories and be very good with your P's and Q's, or actually use the correct accessories, making your life a whole lot easier during this process.
Perfect. Yeah, that is informative. And we do understand that the fibers throughout the world are very much different. It is, though the cores are similar some or other way, but the entire fiber construction might be different. So in that case, if we have a fiber quality which is very low, and and also there is a low power supply throughout the network, how to rectify or resolve that from the splicing standard? How do we do that?
So really the question here, if you have a situation where you're trying to extract all the optical power out of a system and you have a poor quality fiber, I highly recommend a active core alignment, profile alignment system. And I'm going to be frank with you, with the folks in the industry today, all core alignment systems are not created equal. I can tell you from my experiences with the Fujikura product, again, I've been with AFL since 1985. I can tell you that we've had a lot of competitors out there that are coming to the market with some machines that say core alignment. I don't know if I necessarily believe that, because I know the quality of the optics in the systems, and you've got to have a high quality optical system. You just have to have a good pair of glasses, so to speak, so you can get these finite details and pour that core class eccentricity problem and be able to see that. And then the algorithms that are designed to analyze this information and put your splicing XY positioners in the correct position for this core cladding eccentricity issue. So high-end core alignment system, be careful with that. You get what you pay for in the industry. Be cautious, and we'll be happy to talk to you about it if you're going down that path.
And do you need to if you need to run a bidirectional test, how would that be? Would you need two different scanners at both ends, or can you use the same scanner, or are you able to use two different types of scanners?
Yeah, so that question is a good question. So if you have an OTDR scenario, you have a device under test that you are performing a unidirectional test, you have two options. You can use one OTDR, shoot all your fibers A to B, go to the other end and shoot from B to A with that one OTDR, or you have the option, which I think is better option, is have two OTDRs at each location. Do the A to B side with OTDR number 1 and do your B to A splice with OTDR number 2. Send that information up to the cloud. Use your total reports management, what we call flex reports, to generate your report from that documentation. I will caution you though, when you go through this process, make sure that you're identifying your file configurations accurately. So when you collate this data, that the software will pull the correct two OTDR traces and mesh those two data points together to give you an accurate report.
Okay, perfect. Yeah. And where do I add the tail code when I'm testing this?
The tail cord actually goes on, when I say a device under test, it's typically going to be from one patch panel to another patch panel that may be 10,000 feet away, as an example. Under that scenario, the tail cord would be plugged into the B side of that device under test, that patch panel.
Okay. And do our old Fujikura machines help out with the splicers, splicing different kind of fibers?
Say that one.
FSM50 and the older ones.
Okay, I understand. Yeah. Are the older core alignment systems capable of splicing this newer generic fiber? The answer is yes. The older Fujikura core alignment systems going back, I'm going to go back to the 50S, 60S, 70S, and now the 90, certainly has the capability. And that's one thing of interest in this. When we're talking about parameters, splice parameters, there is very subtle difference for what I call finite tuning of different fiber combinations. But in reality, you could use your standard SMF single mode splice parameter and still get fairly good optical results. And what I'm talking about with that, when you're talking about small incremental improvements, you're probably talking about 200th of a dB, 0.02, maybe 0.03 dB. One parameter, your standard SMF parameter versus a optimized parameter for a G.652 type system or a G.657-B3 system. Very little as far as parameter changes.
Okay. And there is one interesting question here. They're asking, they are using one of the Chinese brands, which is called as a core alignment splicer, and they have got some problems with when they're splicing two different kinds. And they're just asking, how is Fujikura machines able to splice two different kinds of splicers against the Chinese brands? What is the main functionality difference?
I guess let me reconfigure that question. The question is, why do you think the Fujikura core alignment system has superior characteristics than the Chinese produced what I call private label core alignment system? Honestly, I think it comes down to two areas. That would be the quality of the optics and the algorithms. I can tell you that Fujikura, their software, they are very security minded when it comes to their software algorithms. They actually produce their own IC chips, manufacture their own integrated circuits for these algorithms. They have tried to minimize any what I would call reverse engineering of that technology, and they've gone to great lengths to protect their copyrighted software.
Yeah, I agree. Yes, and we do have decades of experience in making the technology better and better day by day. So one more question is, do companies hesitate to purchase cables without knowing the manufacturer of the fibers inside? Do you think this concern is justified?
That's an interesting question. Do companies try to stay with the same, I want to call it the same flavor of glass? The answer is yes, but in today's environment, especially, everyone remembers COVID, and we had massive shortages of products coming into the industry. Unfortunately, our customers, I guess fortunately, our customers are very end user sensitive. The customers that they have, they want to turn up the service as fast as possible. So in a lot of cases, they don't really have a choice other than going with this secondary supplier or even a third supplier to get that product in the field so they can turn up their systems and satisfy their end users. So it's a double-edged sword. Yes, we'd want to stay with fiber types and be very selective, but there also may be a cost premium associated with that too. So it's a difficult decision on that side of the fence as well.
Okay. And when you're testing the launch cord and the tail cord, whatever we have between the network, do they need to be the same spec as the network cable, or it can be different? In other words, if you're taking a 652 and the launch cord is a 657, that might affect the entire quality of the testing?
Not really. there are launch cords, if I'm not mistaken, today are what we call them fiber rings. Launch cord, those would be, believe it or not, the 657-A1 variation of ITU fiber. And that is, again, our launch ring is a lot of fiber stored in a very small area of packaging. So that's why we use that bend insensitive fiber. But on the back side of it, what we're more worried about with the launch ring is a precise distance. When we say 150 meters, we want that launch ring to be 150 meters. So the OTDR, when we use a launch ring in a tail ring, we tell the OTDR exactly what those footages are. So they will automatically mask or remove that footage calculation from the device under test equation. So it's more about distances versus fiber type.
Okay. And we do have a lot of other questions which are very specific to some networks, and some of them are to the cable types. So for now, for those, I would say we will just reach out directly to the questions, and we'll answer them.
We will follow up with all the questions is basically what you're saying, right, Meg? Thank you for your time.
Thank you. Yes. So thank you everyone for taking your time and sitting on our webinar. Please feel free to reach us out, and I will give it over to Charlie.
Yeah, no problem. Thank you guys. Thanks, Mega, and especially Craig for the presentation. Thank you everyone for joining in and your questions today. As Craig and Mega said, we had a large number of them come in. We'll get back to you on any that weren't answered. So a survey will be sent out after the webinar, and we appreciate all of your comments on this and future webinars. And a link will be sent out tomorrow also to the recording for viewing along with their certificate. So this concludes our Splicer webinar, and we hope you all have a good afternoon. Thanks again.